in the Department of Electronics and Communication Engineering at National Institute of Technology, Patna. He obtained his PhD from Indian Institute of Technology, Patna, and master degree from Hong Kong University of Science and Technology, China. Dr. Akash served as associate communication and networks engineer at Boeing Research and Technology Department of Boeing India from the year 2019 to 22. At Boeing, his research contributed in development of onboard cabin and offboard wireless communication networks and led multiple collaboration research projects with IISc Bangalore under the Aerospace Network Research Consortium of Boeing. Dr. Akash worked as a senior research fellow in wireless communication research lab at IIT Patna. He specialized in the waveform design for integrated and hybrid satellite terrestrial broadcast system. In the year 2012, he was a visiting researcher in the Telecom and Signal Processing Lab at McGill University, Canada, where he pursued research in the domain of wireless sensor network application in the smart grids. At McGill, Dr. Akash was recipient of prestigious Natural Sciences and Engineering Research Council of Canada Award. His research interest includes integrated and hybrid non-terrestrial network, terrestrial network, 4G, 5G RAN, 4G, 5G and 6G wireless technology. And he has a lot of credential to his repute and published several journal and conference paper at the international levels. So I welcome Dr. Akash and hand over him to deliver his keynote address today FTP session. Over to you, sir. You can share your presentation and go ahead.
Thank you for a very brief introduction. I'm thankful to MNNIT to have given me such a platform to deliver a keynote today in 5G and beyond wireless communication challenges, FDP. Correct? Am I correct? Yeah.
Yes.
So
Yes, sir.
I hope you guys are able to see my screen. So my today's presentation is going to be
Just a
in the
minute,
area
sir.
of
Sir, your screen is now not visible. Please share it again.
yeah, that's what the thing is. That's why I switched off my video. The problem is
Okay,
with the
your video is now not
yeah, the problem
visible,
is
but your sharing screen is also not coming.
it there now? Now is it?
Yes, now it is there. Please make
Yeah,
it
it is visible. Okay,
share.
fine. Yeah, just a second. Okay. If just a second, I'll just have to make it full screen, right? Anyways, I borrowed some other's laptop, so I don't know how to this F5, I guess. Anyways, is the all of you right?
Yes, it is visible.
So fine. Let's begin. If there's anything, then I'll just elaborate it on more and more so that it becomes more clearer. So it's already 11:52 now. So I just begin on with my presentation quickly. So today I'll be delivering a keynote on a very basic thing, that is evolution of 5G technology towards 6G. We migrated from basic technologies, underlying technologies, from 1G to 2G to 3G to 4G to 5G, now upon to 6G. Okay, so the thing is that before moving on to the rolling on to the subsequent slides, I want to make sure that if everyone in the audience, they are familiar with what are standards, because so the first part of my presentation is going to be towards the standardization of 5G, and how we are actually migrating towards 6G through the through the advent of 5G advanced technologies. 5G advanced is another another. I simply put together that what are standards that establish and agreed upon way of doing something. That is, if we go accepted practices to technical specifications or requirements. So what you say that standards help ensure a common approach and repeatable out from industry, consumer networks, groups, and other stakeholders. Okay, so people from all the wide spectrum of the society who are into the world into this technical world, they contribute voluntarily. They come together on a
Sorry
common
to
platform.
disturb you, but your screen is not visible, sir. Sir, your PPT is not on the screen, sir. Please check the share option in WebEx.
Okay, I'm sharing the option again and again, but I don't know how it is. I'm again sharing the screen. Okay,
Yes, sir.
see that.
Yes,
Okay,
sir. Yes, sir. Yes. Yes, yes. Now it is fine, sir.
okay, fine.
Make it full screen.
That's fine. That's fine.
That's fine. That's fine, sir.
Let's go ahead.
Okay. Okay, fine. So I was discussing that from from the perspective of the standards, that what are standards, how standards are developed. Just to give the audience a brief overview that how why standards are important, so important, just not to create an anarchy. That's why standards are important. People from very diverse backgrounds, from who are concerned with the technical world, they come together on a common platform, and they voluntarily develop a, a consensus, a collaborative out of collaborative effort, a single document which has to be adhered and which has to be adopted by everyone throughout industry, throughout academia, and everything. Uh, just to make things to just to be on a common page. So these are the mutually agreed consensus, and the standards are actually important because they enable technologies to work seamlessly. Yeah, they they foster smooth operations across industries and markets, and help us build a common a very uh, 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 easy consumer trust. You know, so standards create mutual understanding actually by distributing knowledge and common guidance across industries and markets. So products and services, they can be designed and manufactured to work together in safe, secure, interoperable, compatible, reliable, and in an efficient way. Oh, I can go on and on all this about standards. So in short, standards are very important in order to avoid anarchy. For example, um, if we go on with the Wi-Fi routers, so there are multiple companies that they develop routers, right? For example, D-Link, Aruba, T-Link. What happens is that if standards are unavailable, standards are not in place, so and if you buy a router from any company, they work similarly. They work identically. If there's a particular band that a router addresses, so that the companies might be different, but the functionality and the technical specifications are going to be the same. So they cannot go and invent and prepare any of the um, any of the hardware which is not actually technically approved by the government, industry, and as per the policies, as per the standardization policies. So that is why we get something which is actually interoperable, and we switch on to multiple companies. Policies and rates can differ, but technical specifications, they cannot differ. So moving on to this portion of evolution from 5G to 6G, it is important for us to understand that what led to the development uh, of 5G and why are we migrating towards 6G. I'll just go and give a little bit of a background on how there was a leap in mobile communication standards, how there was uh, the transition from various standards and up to where we reach towards 5G. So in 1980s, just a historical background. So in 1980s, actually, he started with something called as analog voice, and there were certain standards that were developed to address this type of communication, analog voice communication. So that was an AMPS, Advanced Mobile Phone Systems, then NMT, Nordic Mobile Telephony, then TACS, that is Total Access Communication System. So AMPS actually was developed by North America, NMT was developed by Nordic countries, and TACS was actually developed by Europe. So now the prime concern at this point of time was voice communication. Then there's something we transitioned towards 2G, and that revolution started in 1990s with the advent of digital advanced mobile phone system, which was actually developed by North America. That was actually basically concentrated in North America. Then GSM, global system for mobiles, that was developed in European countries. Then CDMA technology was developed, where IS-95 was put as a core technology behind, core technology to address CDM. So this 2G, it also focused on voice communication, but there was a little towards providing data. That is, we supported data in form of SMS, short messaging services, a very low data rate communication. That was small messaging services. Then from 2G we moved on to 3G. Our focus shifted towards voice as well as data. It was actually the first time in 3G where we saw that there was something which is called as video streaming. There was something which is called as high speed data communication along with voice communication, because the bandwidths were considerably higher at that time. So the technology that evolved, the standards that evolved, CDMA was evolved to CDMA 2000. GSM, it got evolved to EVDO, evolved, EVDO, then the wideband CDMA, then high-speed packet access HSPA. So all these standards, they have developed and they have evolved, and they are actually suited to wider bandwidth communications to support high data rate communication. I just want to reiterate that wider bandwidths, they directly equate to higher data rate communications. Then there was the demand for data became even higher, and to address that market demand, we switched on to 4G systems that basically that saw their initial research and existence from to 2010s. During 2010, we saw that there was the advent of 4G communications, and our focus shifted mostly towards data communications, where there was mobile broadband and emerging expansion at that time, and we are actually still until pre-COVID, we were actually using LTE phones, long-term evolution and long-term evolution advanced phones, and gigabit LTE. So high-speed data communications, we moved on to even higher bandwidths to accommodate the voice and data services together. Then there is an era now. There's an era now where voice, data, communications are they are sufficient, but in addition to voice and data communications, there is something which is called as Internet of Things communications. Like there are multiple massive low data rate devices, massive connected devices that actually send small amounts of data, and they want to be connected to the web, to the internet. So 5G standardization is actually the era of connected intelligent networks, collected intelligent networks, Internet of Things. So far, till 4G technologies, we did not focus towards the standardization of IoT, Internet of Things, and the standardization of smart connected devices, or devices with low energy, and the communication of small amounts of data. Now there has to be something which needs to be standardized in order to bring different companies, industries, and academia on the same page, so that they can adhere to certain guidelines in preparation of the hardware, in preparation of I mean, to be on the same page, to be connected to a particular network which is in place, and which has been mutually agreed as per the standards. So 4G standards, actually they started from release number 18, and the standardization body was is actually 3GPP, third generation partnership projects. And then 5G, it started from release number 15 in the 3GPP standardizations, and started when nearly about 2015 2016. And then we'll be moving into 6G, which might be a technology that is that we might see the first standards coming by 2035 or 2040 maybe. So from connected intelligence to AI, artificial intelligence. So migration from 1G to 6G, in conclusion, it entailed communication, like voice communication, then voice communication modified to voice and data, then voice and data modified. Yeah, they were they were added with the IoT, then voice, data, IoT, as well as artificial intelligence. So this is actually the migration of mobile telephony through several decades. So it is not very hard to realize from 1G to 2G, the bands were from 800 to 900 megahertz, and also in fewer lower and higher bands. 3G and 4G spanned from 450 megahertz up to sub 6 gigahertz bands, and the 5G, the standards for 5G, that is frequency range 1, it is actually sub 6 gigahertz band, and up from 24.25 gigahertz to 52.6 gigahertz. Actually, these numbers are important just to give you a flavor that when we move from one generation to higher generations, that is one common thing that is always present. That is, we move from lower frequency bands always towards the higher frequency bands, because in order to incorporate high data rate communication, high speed broadband communication, we need higher bandwidths. But everything has its pros and cons. So higher bandwidths, they have problems with channel estimation and stuff like that in the physical layer. So that is not the point of our discussion as of now. So there are certain, like I said, that there are certain standardization bodies. For example, like for mobile telephony, the standardization body is 3GPP, and like for Wi-Fi technologies, the standardization body is IEEE. So simply, so 3GPP documents are actually, for each and every releases, for each and every developments, each and every evolutions or technological developments in the technology, 3GPP releases the documents in, yearly. It releases the documents yearly, and each, these documents are actually divided into releases, and each release actually incorporates new features compared to the previous one. 4G, as I said, that is actually defined in release number 8 and onwards, and for release number 15 is actually known for 5G new radio 5G NR. So the 5G technical specifications are organized in multiple series. For instance, like series number like 38 series is now documented for transceiver design aspects for NR. My area of research is actually the G node B, E node B are the physical layer aspects of 4G and 5G technology. So for me, the release number 38 is more important, and I focus more on this. And like before moving precursorily, I just want to give a brief overview of the 5G network architecture, because we have projected, we have cruised from giving a brief introduction about the standards. Now, on a very higher level, that what is a 5G network architecture? So you see that there are user equipments. There is a user equipments. We can consider them as mobile phones that we have in our pockets. This is something which is a base station. This is a baseband unit, and this is a 5G core. So what happens is that the combination of this base station, which is also called as a remote radio head, and the baseband unit, they form something which we call as G node B. G node B. Initially in 4G, we used to name this same thing as E node B, that is evolved node B. So this is a terminology which is given to 5G new radio, and this is the combination of remote radio head and baseband. So what happens is that in downlink, the mobile phone, they send information to G node B, which is actually processed by the 5G core. 5G core is basically for authentication and billing services. So this is actually, this entire portion is actually the physical layer technologies. These are the physical layer communication from UG to baseband, then from a front haul fiber to the baseband, where the signals get processed and then they are sent to, it's in conjunction with 5G core. They move ahead for billing and authentication. So this is what a 5G architecture comprises of. There's a there's a access network. This is called as an access network, and this is a core network. So the combination of network, 5G network or 4G network, it is actually an access network as well as a core network. Access network always takes care of the communication or the front end communication, mobile communication, radio communication, what you say, or yeah, the radio transceiver designs, or yeah, radio transceiver communications. And there's something which is called as a core network. So in combination of access network and core network, we say that there's a complete network architecture, either a 4G network architecture or a 5G network architecture. Yeah, this is a 5G core. In 4G it is called as an enhanced packet core, EPC, and this is the access network for the 4G technology. So 5G technology is actually 5G, the advent of 5G, it is actually developed in two different designs. You must have heard of 5G non-standalone and 5G standalone. So 5G, just an introduction, that 5G non-standalone is actually based on the 4G LTE core network. Only the difference was in design and development of access network. I'm talking 5G non-standalone. Then there came something which is called as 5G standalone. Standalone technology. It said that the core is actually a new core, which is a 5G new core, as well as the access technology. So non-standalone technology and standalone. 5G non-standalone and standalone. These are two variants that 5G came into existence. So I am actually these are all the prerequisites before starting my presentation. So now what happens is that we will concentrate in this PPT from 5G, from the evolution of 5G technologies towards the standardization of 5G, towards what are the key features that have been incorporated in the 5G technology. And then we will study some of the features, some of the physical layer technologies that are to be standardized in 5G, and that could be the candidate waveforms, your candidate technologies for 6G. Okay, so step by step we'll move. So this is an illustration of the 5G timeline for 3GPP in 3GPP as per the 3GPP documentation. So there was a 5G workshop that was held in 2015, and it was actually we sow the seed of the development of 5G. Then towards 5G 16, there was the release has been put forward as a study item. Then release has been 15 has been put as a work item, and it has been published as a work document, or what you say, that the standardization document. Then there is something release 16 started in 2019, 20, then it has been pushed as a work item, and then there's a 17, it has been pushed as a work item. And then until 2023, there we came where there was a start of 5G Advanced. The 5G Advanced is actually is the most recent standardization, because a technology, when it starts to develop, like for example in 2015, it is quite immature. When the technology over the time, it has been assessed, it has been used, it has been studied and researched. So the technology gets evolved and it gets matured. Okay, so 5G technology got matured over the years, and by the end of 1 decade, approximately, we are studying in 2025. It's 1 decade now. So we are standing at around in release number 18 and 19, which is actually the core specifications release. We are expecting the release for 5G Advanced, some of the key features that will be incorporated in 5G Advanced. So what happens is that release 15 actually, as we said, that it all began in 2005, that the framework for LTE was actually, initially it was designed to optimize data throughput and voice over internet, actually data throughput and voice over internet. And then there were some vertical services, some extensions that were developed in 4G that were device to device communications, vehicle to everything communications, and actually there was something which is called as machine type communications that was incorporated in already in 4G. Now 5G was actually developed for these three use cases, to incorporate these three use cases only. What are these? That are enhanced mobile broadband, then massive machine type communications, and ultra reliable and low latency communications. Enhanced, first of all, enhanced mobile broadband. We are hungry for, for high speed communication. We are greedy people. We are hungry for high speed communication. So enhanced mobile broadband for high speed broadband services, any wideband communications, broadband communications, wideband communications. Massive machine type communications. What is massive machine type communications? That we have already discussed, that a large, very massive amounts of devices, massive number of devices, with those are ready to share very small amounts of data, right? And that data should be incorporated and processed in the network. So that is massive machine type communications. 5G is actually has allowed small devices, like for example, wearable devices, sensor devices, Internet of Things, to be connected in a standardized fashion, in a regulated fashion, as per the government norms. That's what we have discussed. What are standards? Mutually, as per the mutually agreed technical specifications, they should be connected, and they could pass on information in the network. Then ultra reliable and low latency communications, that is like precision, like probability of error to 10 raised to the power minus 15, and low latency communications, that is without any delay. For example, we are actually looking into some of the applications such as driverless communication, driverless automobile services, for example. So these are some of the very critical applications where we can imagine ultra reliable and low latency communications, that there is no there's no what do you say, scope of error. There's no scope of error, as well as if you pass on some information that has to be incorporated without any delay. So ultra reliable and low latency communications. So what happened is that the first release of 5G that we are discussing, it introduced actually a solid baseline for rolling out 5G. First, that I already said that 5G has been incorporated as non-standalone and standalone services. So one easy aspect of 5G standardization is the easy migration from LTE to 5G in commercial deployments, basically. So release number 15 that we are discussing actually was designed to be a unified and very what do you say, very accommodating and very flexible in consideration of the different performance requirements. For example, like in terms of throughput, reliability, latency, coverage and capacity for different use cases. It is actually also very scalable, easy adapting to different spectrum and services. And we've already discussed that what is FR1, the frequency range 1, and what is frequency range 2. So now going on to release number 16 and 17, it actually addressed some of the necessary enhancements as continuation from release number 15, and as well as adding capabilities for various vertical segments. So you see that massive 17 MTC support is particularly actually accommodating eMTC, and it's enhanced machine type communications, narrowband IoT into 5G, and introduction of reduced capability red cap users equipment. The reduced capability, by the way, there's the devices that are small in the nature, the small devices, and they share less amount of information. So for example, the wearable devices and surveillance cameras and industrial sensors. So these for the first time they are being we see such features in the standardization documents for release number 16 and 17. Unlicensed and shared spectrum, for example, uh, bands lower than 5 gigahertz. We saw the standardization of of communication in the unlicensed spectrum. Then for the first time, non-terrestrial communications, that is that is the satellite communications, the web, which support both the enhanced machine broadband services and MTC services as well. Imagine connecting the satellite communications to the wearable devices. You see, again, initially we began in 1980s. We began with voice, 2G, which is voice plus slightest of data, 3G, voice and data properly, 4G, data is actually much more prominent in voice than voice, 5G, voice plus data plus the era of of machine type communication device. In machine type communications, there plus the incorporation of IoT, correct? Then technology, the structure of the standards, they are getting they revolutionized. We are actually moving ahead with towards more towards maturing the 5G technologies, and we are actually, as per the needs, as per what we as per the market, what as per our needs, we are incorporating the vertical segments, such as the segments from the automobile industry, satellites, and Internet of Things. All of these needs to be standardized, right? So they have to fall they have to fall on the same page. They have to adhere to the certain guidelines, the technological guidelines that are being enforced. So non-terrestrial networks, for the first time, we see that they are being standardized in 16 and 17. NR side link supporting the V2X, that is, and side link, NR side link, that is communication between two devices without the need of base station, direct communication with two devices. Public safety network control interactive services, and URLLC, the ultra reliable low latency communications. And for the first time, there is something which is called as industrial Internet of Things, that has been incorporated in release number 16 and 17 in 5G. Now, industrial, we knew one of the term about the term which is IoT, and industrial IoT is which is more specific. So in nutshell, if I have to conclude so far, so we see that at the standardization process, then following the standardization process, there are certain technologies, there are certain use cases. What do we say? Use cases that are as per our needs. For example, voice ho gaya, data ho gaya. Now there are massive low power devices sharing small amounts of data. उनको भी standardize करना है. We need to incorporate them into the network, but in a controlled way, in a regulated way. Okay, fine. So there were studies happened, and the guidelines have been set key, this is the way that we can do that. Fine. Then what about the unlicensed spectrum? How to, if communication is happening in unlicensed spectrum, regulated, fine. Then the incorporation of the there's one use case which is the satellite communications. Okay, we can incorporate the satellite communication and connect it to the 5G network, but in a controlled way, in a regulated way. So this is what we are moving towards, like what is up, like as per the needs, we are incorporating the technologies and the use cases, and then moving ahead. Now, 5G advanced, which is the most recent thing that has happened so far. This I've read that I'm quoting the source, which is 3GPP documentation, and this is the release which is in what we say. This is in production now. Already research has been done. Policyholders, stakeholders, industry, government, everything, they have given a nod, and now it is in the process of you know to come out as a release. Like you see that there's a press release. So similar to the press release, 3GPP also releases the documents on its webpage for public usage. So you see that some of the key use cases, we say that we integrate satellite, non-terrestrial networks, as which has been discussed in release number 15 into the 5G system. Support of Internet of Things, machine type communications, including satellite coverage. Sidelink, proximity, location, and positioning. This is something which is incorporated in this. Then supporting industrial needs, verticals, industries, factories, multicast and broadcast services. Then network slicing, uncrewed aerial vehicles. Okay, fine. So far we have not discussed anything about the UAVs and UCAVs. This release number 18 or the 5G advanced, it sees some of the incorporation from UAVs as well. Energy efficient devices, artificial intelligence and machine learning is also on the portfolio of 5G advanced specifications. Correct. So it is very interesting to note that from where we started in 1980s and in 50 years, where are we so far? So we are actually incorporating things and maturing the technology for our usage. Augmented reality, immersive communications. These are the parallels which no one never assumed that they come under a single umbrella of regulation. So this is, in a nutshell, would say that we started in 2018 and then released 16, 17, giving new verticals, deployment use cases, spectrum uh, towards this 2030 to 2023 and longer term evolution to deliver on the 5G vision. Then next technology leap for new capabilities and efficiencies in 6G, which we will be discussing. So what as uh, as I've already discussed, that my area of research is more towards the transceiver design and physical aspects, and towards focusing on series number 38 of 3GPP. So we will be discussing more on the physical layer waveforms and the aspects, what some of the waveforms of what can be incorporated in 5G and what could have been in subsequent slides. Fine. So you know so this is so far what we have discussed from the evolution of 5G, starting of the nurturing of 5G, and then moving ahead towards the maturing of 5G in different technical aspects or technical regulations and specifications. Now what happens, what they there are speculations that um, that 5G has been already been matured. So what about the future technologies? What could be some of the future trends? What could be the future needs? Based on those, we can start our research and study so that we can move towards the first release of 6G. 6G. So there are some of the combinations. So people thought that, okay, fine, when 5G has been actually been introduced for three use cases, that is enhanced mobile broadband, machine type communications, and ultra reliable low latency communications. What happens if these some of the applications, yes, some of the applications, if they might arise in future, that may use some of the combinations of all these, like for example EMBB and machine type communications, they can be mixed together. Like, is if we can think of some application कि जहाँ पे high speed data communication is needed, high speed communication is needed in conjunction uh, where machine type communication is already present, where some of the use case devices and some of the low lying devices, yeah, low power devices with sharing low amounts of data, they are present. So high speed communication with that, where there can be some of the applications where high speed internet, yeah, high speed services are required in conjunction where reliability and latency is paramount. Correct. For example, space technology. So we send some of the signals in space. So if the 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 device or the station or the satellite is far away, is very far away, so it takes a certain amount of time from the satellite to signal to go to the satellite is come back. So it creates a little bit of a latency. So now what happens if the GPS positioning or high speed communication in the trains, it is happening at the ultra fast speeds. So this latency might create some problems, right? So we are in the era of delivering fast services. Everything is actually moving. Everything is actually moving is in the process of getting very faster and faster. Trains are getting faster. Your automobile industry is moving faster. Technologies are getting more evolved, more and more what do you say matured these days. So the use cases in combinations of one another, they can be some of this can be an approach towards the standardization of 6G. And this is as per the industrial thought or industrial thinking. I am quoting the source from NTT Docomo. Actually, this is a company from Japan. So they are in the process of standardization towards 6G from this particular approach. If I say in nutshell that what is 6G, 5G का तो समझ में आ गया कि that so far that this is what we are towards maturing of 5G. So उसका तो समझ में आ गया that from we started from something, there were certain use cases, there were certain needs. We try to regulate those. We try to we acknowledged those needs, and then based on that technology, we try to incorporate certain regulations to to incorporate them in a controlled way. Now what happens is what is 6G? What is 6G? What else can be done in 6G? By artificial intelligence and machine learning incorporated, NR side link incorporated, proximity and location incorporated, accuracy incorporated, ultra reliability is incorporated, low latency is incorporated, machine type communications is incorporated, and then voice or data to hey. So what else remains in 6G? So there are some different industrial revolutions. Yeah, different industrial, what do you say? Different types of industries. They have different visions actually towards the standardization of 6G or how they perceive 6G. So one example I'm showing here is that when these these use cases are in conjunction with these use cases are in combination of one another, which is actually the basic underlying use cases of 5G. So we'll move towards something from the generic point of view towards something which is on the physical layer, some of the key technologies in the physical layer, which actually serves as the foundation for 5G advanced. Number one is massive MIMO. Then we will project and see, we'll give an overview of millimeter wave MIMO, then NOMA, then FBMC filter bank multicast. Some of these prominent technologies that find their existence in 5G advanced can 5G can find their existence in 5G advanced plus, maybe something like that. LTE advanced, LTE is LTE mature to LTE advanced, then LTE advanced plus. So I am predicting that 5G towards 5G advanced and then 5G advanced plus until the advent of 6G as the first release. Maybe एक और बात कि from 1G to 2G to 3G to 4G to 5G देखा जाता है कि approximately it took 10 years for one standard to be released or to be adopted. 1980s में 1G था, 1990s में 2G, early 2000s या late middle 2000s में it was 3G, 4G remained until 2017 2018 और अब 5G. So as per the historical evidence, I see that by 2028 or 2030 we should be seeing something as first releases for 6G, correct? And then there are certain aspect, we have already, many countries, they have already began work on 6G technologies. For example, जैसे वो था जैसे Bharat 6G Alliance, we are working in collaboration with multiple IITs. Then China, they have already set up a task force, which is what I remember it is called as China 6G Wireless Technology Task Force. And then in US, there's a next generation alliance that already developed in 2020. North American leadership in 6G. Then Japan, if I remember that it is beyond 5G promotion consortium in Japan. Then something there's in Europe, Hexa X project. So all these countries, all these the developed countries, they've already started their research, their investments, their their standardization procedures in the area of 6G already. They've started. India is in that country under the leadership of Prime Minister. We started in 2023, which is actually almost 3 years late from China. China started in 2020 already, and the US started in 2021. Japan started in already 2020. Hexa X project already started in Europe in maybe around 2020s and 2021, something like that. So the very latestly, very recently, we began our research in 6G. 5G testbed in IIT Madras is already in place already. We'll be seeing the first we are the first like, preliminary research upcoming in the area of 6G very soon by around 2027 2028. Anyways, so we'll see we'll move on to some of the key technologies. We'll start with massive MIMO. So I hope some people in the audience, if some of them are PhD or master students, they understand that what is the concept of MIMO, multiple input, multiple output. Historical evidence, you see that it has been developed by an Indian, which is Paul Raj, Arogya Swami Paul Raj. He is actually an emeritus professor in Stanford right now, and that he actually retired as a naval officer from India. And he then he went ahead and developed this particular technology for which he's been awarded the Turing Award, which is actually parallel to it's a very prestigious award. People call it as a parallel of a Nobel Prize, right? So this is a very classical technology, MIMO technology. What happens is that you see there's this the concept of beamforming written in the vertical and the horizontal direction. So what happens is when we transmit the signals, there are multiple antennas at the transmitter and multiple antennas at the receiver. What happens is when we transmit the signal and we make sure that the phase shifts from each and every antennas are in such a way that signal they do a constructive interference and they combine and they give a proper amplitude, a proper signal in a particular direction, and that is what we call as a beamforming. So the types of beamforming, there's analog beamforming, digital beamforming. There are multiple services. Classical beamforming, which we usually do, which is maximal ratio transmission, usually, which is a very classical and um, very form of beamforming, which is maximal ratio transmission, where we assume that the channel is known at the transmitter, and we design weights according to those channels, so that when the signal is passed on to the channel, they combine in such a fashion so that they have constructive interference at in a certain direction, in a particular direction. So what we do, as per this technology, what you do, you can feel, you can imagine that your signal is concentrated at one point, and there's a sweeping of the signals that is going on across across the three dimensions, sweeping of the waveforms in the three dimensions. One of the classical examples that I have come across is actually MIMO. When multiple transmitters and receivers are present. So if you imagine there's a cricket stadium with 50,000 people sitting in one stadium, and see that if the wireless towers surrounding that cricket stadium, they are very less, because the RF engineers never imagined that some like 50,000 people or 1 lakh people will be gathering at certain point of time, and they will be giving access high-speed broadband services to all those people. Some of them will be video surfing, some of them will be doing some chat, WhatsApp chatting and YouTube services and whatever it is, high speed communications, or the high speed demand might surge at that point of time. So what happens is that multiple base stations, what they do is that they can do some sort of beamforming, and they concentrate their entire energies or entire resources in one direction, which is pointing onto the cricket stadium and providing services to them on the same end, on the at the same time providing no services to the adjoining areas this can be a hypothetical case, but this is some of the example. This can be an application of something which is called as which we call as beamforming services. So MIMO, again, technologies mature themselves. So MIMO was actually developed in maybe somewhere around 2000s, and now we see something which is called as multi-user MIMO. There are certain variants of MIMO. So, SIC multi-user, successive interference cancellation multi-user MIMO. Many other variations of MIMO. So I just to give a brief overview, we see that this is called as multi-user MIMO, where multiple users are given certain bandwidth or certain resources in the network to perform this particular action, and there can be a beam sweeping in all the in the three dimensions. Correct. So this is a very on a broad level. This is a concept of massive MIMO. There's a concept of millimeter wave MIMO. So millimeter wave MIMO, the millimeter wave. When we understand what is millimeter wave, so it automatically comes into our mind that there might be a band which is above 30 gigahertz. के बैंड से ऊपर, KU बैंड से ऊपर 30 गीगाहर्ट्ज एंड अंटिल 300 गीगाहर्ट्ज, मतलब तकरीबन 0.3 टेराहर्ट्ज के बराबर है जी. तो moving from 330 gigahertz to 300 gigahertz. So what the problem with the higher bands is actually the attenuation in the signals become very high, and the signals cannot propagate to a very larger distance. But at the same time, higher bandwidth, higher spectrum, very, very wide bandwidth, they support high speed communication. Higher bandwidth is directly equated to high speed communication, high bandwidth, high bandwidth, high speed communication. So see that this is actually a 5G candidate network architecture, which is based on millimeter wave massive MIMO. So you see that the architecture is actually a multi-tier cellular. This is a heterogeneous network. The multi-tier cellular HETnet, which is composed of a macro cell and small cell base stations. With massive MIMO, this something called this microwave and millimeter wave communication. It's a combination of microwave and millimeter communications. So this is it features several scenarios that are subjects of ongoing research in realizing the 5G goals. Right. So there's something which is called as a dual mode or a dual band small cells, where close by users are served by millimeter wave links, while farther away users, the closer away users, they are using millimeter waves, and farther away users they are using as they're being served by the microwave frequency band, thereby serving as a dynamic cell. And and it is actually imanting as a cell breathing concept from the legacy networks. So closer users, wider bandwidth, but the frequencies are very high. Farther away users, frequencies are lower, and but the distance becomes very high. So see that the massive MIMO antenna array, multiple antennas in the array which are doing beamforming services, and there are beams which are very narrow. These beams which are very narrow, and they are not creating interference amongst the subsequent areas in the 2D. So pencil beams, what is a pencil beams? So very narrow beams to very longer distances, and then giving access to certain particular patented locations. In 6G, this can be a use case where the accuracy or the positioning is very important, and if you are able to provide services to a particular set of to a particular region in a few meter square region, and concentrating the energy from the antennas in a particular region and providing services to that. So you can imagine that a person moving, or for example, a train is moving or the bus is moving, and you're continuously following that bus as per the beams, and providing the connectivity all together during the entire journey. This can be a particular case. These are all also what we are discussing is all very fancy and hypothetical concepts, but they can have the face of reality someday, maybe. Again, there's a concept of NOMA, non-orthogonal multiple access. People must be knowing in the audience that this is actually different users are actually given different power levels before getting multiplexed. In the multiple access cases, multiple users, they are fed as they are actually modulated with different power levels, and they are multiplexed together. And at the receiver, what happens is that we identify the strongest user first, and then we use a successive interference cancellation from the weakest users. See, we identified the signal detection with the user which has maximum power, and then SIC is used in order to chop off the interference from the weakest users, and hence we have detection from both the users. Now, if this particular user, non-orthogonal multiple access, actually is what happens is that when it is actually, see, again, clubbing of technologies, amalgamation of technologies. NOMA is clubbed with MIMO, what happens? NOMA is clubbed with MIMO. So you see that multiple users in MIMO with different power levels and using and enjoying different specific beams of communication, concentration at certain points, at the same time getting segregated in terms of power level. See, so the different users in the different beam concentration areas segregated in the power levels. So now the amalgamation of technologies between NOMA and MIMO, combination of NOMA and MIMO. So this is basically, this is actually I am quoting the concept of power domain NOMA. There can be other sources as well. Again, there's a concept of FBMC, filter bank multi-carrier. We started in 4G as 4G. In 4G, we introduced the wideband communication, and to address the different challenges in wideband communications, we brought a modulation technology which is called as an OFDM technology, orthogonal frequency division multiple access technology, in order to counter some of the shortcomings or the cons of transmission in the wider bandwidth. So what happens is that you must be knowing that if we send a pulse in OFDM on different subcarriers, so what happens is that pulse will spread on to have a sync waveform as an impulse response, and then the sync waveform, what is the nature of the sync waveform is actually, or any other order the raised cosine pulse that we are sending, there's a nature which they will be have an out of band radiation, out of band splitting, or out of the band spectrum already. So what happens is that this was a problem that was encountered in OFDM in 4G. Now, as the technologies, they matured themselves. OFDM is actually matured. So there's this one variant of technology where we use filter bank multi-carrier. That is for certain users or for a single user. Again, the variation. We put a certain designed filter, which is also called as a FIDAS filter, and we try to curtail the out of band radiation so that the interference from one subcarrier, they do not impact the interference, or they do not impact the communication into, or they do not spill over into another spectrum of subcarriers. So this is why this is one of the core concepts of FBMC. Later on, we do not use cyclic prefix, and we save our spectrum, and then we do communication, which gives you a high data rate communications as directly by changing the architecture of the OFDM. And so this is all it is. It's just a core technology. So what this is saying, that every signal is coming, which is actually being passed through a filter, and again, simple baseband to passband communications, and then sending to the channel towards the receiver. So this is actually on a very higher level. This is a block diagram of a filter bank multi-carrier transmitter. Now, again, what we said that from the context, from the perspective of physical layer technology, from the perspective of physical layer technologies, FDMA 1G, 2G में TDM है, 3G में वाइड बैंड CDM है, 4G में OFDM बेस्ड माइमो टर्बो कोडिंग और IoT, 5G में भैया क्या आया, OFDM बेस्ड सेंटीमीटर वेव, मिलीमीटर वेव, मैसिव माइमो, LDPC, I mean polar coding and turbo codes and whatever it is. ELT. What is the radio access technology? Future RAT, radio access technology. What is the future radio access? भाई OFDM हो गया, वाइड बैंड कम्युनिकेशन में जो भी प्रोस एंड कॉन्स थे, that OFDM has already taken care of that. We have matured, we have evolved, the OFDM has evolved to its best possible, to the best possible variant already. We have done channel estimations, we have mastered equalizations, we have mastered many of the technologies, or many of the many of the shortcomings that are present in these technologies for wideband communications. What's next? So this is what's next. Either people say, this is what TT Docomo says, an industrial thing, that what it says, that OFDM based, yeah, koi new waveform with centimeter wave or millimeter wave, or new waveform that can fit into for centimeter wave communications or a millimeter wave communications or a terahertz, or कोई ऐसी चीज, वो कोई टेक्नोलॉजी which has extreme coverage, new network topology, further enhanced massive MIMO, enhanced ultra reliable low latency communications, या फिर you want to move ahead with AI, want to move ahead with AI and try to develop something from the AI point of view that has an impact on the radio access technology, that has the impact on radio access technology. तो ये कर सकता है. There can be multiple approaches. So one approach that we have already discussed in the previous slide, that is the combination of different use cases that are already present in 5G. For example, enhanced mobile broadband services को अगर हम ultra reliable low latency communications के साथ merge करते हैं, तो अगर कोई ऐसा application evolve करता है, तो what happens? Now, future radio access technology is something which is it can have a predecessor from low-lying technologies, predecessor from low-lying radio access technologies, 3G, 3G, 4G. We can pick some of the technologies and make it more mature and bring it into 6G. We can learn from how we started and how we tried to develop some of the technologies as per our needs in different during the different phases of what do you say, of the development of standards, during different phases of the development of standards. So technology, we can use it, whatever it is. So it is up to the level of discussions as of now. 6G technologies is at the level of discussions as of now. If we go and look into the IEEE Explore and we search some of the surveys and tutorials papers, so we see that there are some assumptions, some discussions, some proposals. Assumptions, discussions, and proposals. But there's nothing which we call as concrete. Ki bhai, this is something which we can see as a future radio access technology as a candidate into 5G or into 6G. Right? So this is on a very broader level, that is the evolution of mobile communication systems towards 6G. And 6G, there's a question. Fine. So there are certain reasons that why we need to migrate from 5G to 6G. We need to push the communication to higher frequency bands. जैसे मैंने पहले भी कहा था कि that 1G to 2G to 3G, 4G, 5G, very common that we are actually increasing our spectrum in order to incorporate higher data, high speed communication, higher bandwidth, high speed communication. That's it. Creating smart radio environments, so reconfigurable surfaces, making our our communication or our communication environment more intelligent. You know, this is an era of intelligence. So one scientist said, Qualcomm, this is a scientist from Qualcomm, I don't remember them. He said that 60 it will be the era of connected intelligence. That is AI for everyone, AI everywhere, you know, artificial intelligence. So his perspective, his point of view is the his perspective is in the development of AI, or he sees that AI could be the future. While Entity Docomo thinks that AI could be a candidate, but radio access technologies from the predecessor communication as per the needs from the market, or as per the needs, or as per the applications, this could be one possible way to move forward. Fine. So creating smart radio environments through configurable surfaces. This is something which I have also read in literature. Then removing conventional cell structures, and then, you know, up, we have already studied there's a concept of cellular communication. So can we move towards cell-free communication, cell-free massive MIMO? There's no cell, like the concept of cell breathing, you know, as per the needs. Cellular structure is defined as per the traffic, adaptive. Okay, so 6G technologies I wrote it will rely on. I say that it might rely on millimeter wave technologies, that is from 330 to 300 gigahertz. Terahertz technologies, 300 gigahertz, where millimeter wave exhausts. वहां से we will start 300 gigahertz to up to 3 terahertz. You know, there's some. I'll show you that there's a paper, there's a research article written by Rappaport himself about these terahertz technologies. I'll demonstrate that. Free space optics. Free space optics. There's something which we call as quantum communications as of now. So it is the concept which use quantum technologies. Yeah, you know, QKDs, quantum key distribution. It needs free space optics actually. Free space optics means in the space. So in nutshell, requirements for 6G: extreme high data rate, capacity, extreme low latency, extreme coverage extension, extreme high reliability, low cost, massive connectivity and sensing. So हमको सब चाहिए. We need everything. We are very greedy people, right? So we need everything which is to the best, and for which 5G is still struggling to achieve. This is what we need in 6G, and we need to push ourselves to the extreme ends, and the regulators, all the stakeholders from the government, policymakers, they have to stretch their arms and stretch their understanding of networks they have to bring something which is where all these things can be possible. Fine. So this is what I'm saying. So I'm quoting each and every of my slide. They have certain certain essence from the industry. Either I'm quoting Qualcomm, or I'm quoting Entity Docomo. And this is also what do you say, that this is also a vision. This is also a vision from the industry. Now, some of the key, what I feel, as I also this is my research area. I also feel that these could be some of the key technologies based on 6G. You know, key 6G technologies. First technology, which is called as OTFS, orthogonal time frequency space, terahertz communications, visible light communications, and intelligent reflecting surface. जिसमें से first and fourth is something which I focus mostly on. Terahertz communications is something which is still in picture, but इतनी high frequency के लिए it is difficult to realize at the level of hardware. No, such high frequencies at the level of hardware. So doing experimentation at the level of hardware, it's a little difficult. You know? So OTFS and intelligent reflecting surfaces, IRS. So what is the concept of OTFS? Again, the mother waveform. The mother waveform has always been OFDM. So as per NTT Docomo, what I said, that radio access technologies, it will take certain waveform from the predecessor technologies, underlying technologies, and bringing it forward and making there's something which is ultra usable, as per today's needs. OTFS. This is the waveform which is actually designed for high mobility communication, very high mobility communications. OFDM, what happens is that the mother waveform OFDM, the architecture for OFDM fails when we when there's a very high speed communication, or when the intermediate wireless channel is changing very fast. So the inherent architecture of OFDM fails, and we get something which we call as inter-carrier interference. Already we all know about that. These are all basics. So now there's a concept of OTFS, orthogonal time frequency space. What we do is that we, instead of sending our signal as a time frequency signal, we send our signals. We imagine, we treat our signals, we process our signals in something which is called as delay Doppler domain. As per the channels, as per the time varying nature of the channel. So there is something which we call as delay Doppler domain. So this is what is the underlying technology behind OTFS. In this process, what happens is that the OTFS solves some of the two basic problems in OFDM, that is the Doppler effect as well as the subchannel gains, because they're not equal, and they create something which is low signal to noise ratio. So it solves some of these two problems, and it works in the delay Doppler domain rather than the time frequency domain. So this is the concept which is developed by the industry. The name of the company is Cohere Technologies. COHERE, Cohere Technologies. This is for the first time it has been developed by Cohere Technologies. So I say what we do is that we do, despite of doing inverse fast Fourier transform, we do something called as inverse symplectic fast Fourier transform, and then at the receiver we do a symplectic fast Fourier transform. So this is a special type of transformation which converts the time frequency, or the delay Doppler frequency, delay Doppler domain into a time frequency domain, and then vice versa. So this is what OTFS does. Again, the underlying waveform is OFDM. Uske baad we moved on to FBMC. Then we took a parallel branch, and then we moved into something called as OTFS, orthogonal time frequency space. Terahertz band communication, terahertz band allocation. So before moving into this slide, we see that at the foot of this, written by T.S. Rappaport, we read the book of wireless communications by Rappaport, right? So this is a paper by Rappaport himself, Terahertz wireless communications, co-sharing for terrestrial and satellite systems above 100 gigahertz. And this is paper which has been published in IEEE Communication Letters in 2021, very recent paper. So see that there are certain bars. What he did is that he assessed the entire spectrum. He mentioned that because that on certain technologies, on certain frequency carriers or certain frequency bands, there is a very high path loss. What happens when the frequency becomes higher than 10 gigahertz? There is something which is called as molecular absorption, water absorption, or signal gets attenuate in the air, and there's an air absorption. So those, it becomes very high at certain points, at certain different points. You see that this black curve is showing the path loss. So see that he did experiments from up to 260 gigahertz and found out that on certain frequency bands it is impossible to communicate signals. It's a very good paper, and it is actually of practical relevance as well. So you see that 100 and after 130 to 140 things are okay, and it gives you around 32.5 gigahertz of band. 32.5 gigahertz of my band equates to how much? The bandwidth is 32.5 gigahertz. It's ultra massive. It is actually used. It could be used for ultra massive high speed communications. For example, पूरी की पूरा YouTube के documentary you will be able to copy in 1 second of time. See, so this is what it is. But the problem with terahertz communications is that the signals will die off in few centimeters, or maybe maximum up to, if you do communicate up to 1 meter or something, because the wavelengths are very small. So that is the problem. So for an office area, for a closed surface, or for an indoor environment, this technology is good. But for external purposes, the signals will undergo a lot of deterioration, path losses, and hence it won't be an efficient technology for outdoor communication. So this is what Rappaport said actually. Visible light communications. So visible light communications is a code source which is actually from IEEE standard itself. I'm writing the source with IEEE. So we say that it says that they comparing with distance and data rates. Again, the problem with distance, right? Distance and data rates. So ultra wideband communications. You see 802.11, 802.11a and b. This is why these are Wi-Fi standards. So see, significant high data rate communication as well as for a longer distance. This is Wi-Fi. But Jesse, when you go with visible light, to visible light, there's a boundary attached to that. Okay, in meters, it cannot go beyond 5 meters. Visible light communications. But yes, data rates. This is 100 megabits per second, 480 megabits per second for a very small distance. But very high data rate communication is possible with VLC. No, this is infrared, VIR, FIR. So Bluetooth and Zigbee. Zigbee is actually a standard. This is an IoT standard, wireless sensor network standard, Zigbee standard. IoT, basically it is 802.15.4. Yes, IEEE 802.15.4 is a standard for Zigbee. Bluetooth, this is a different standard. So also this is a Bluetooth standard itself. So see that Bluetooth data rates are for few distance, for few tens of meters, and a very small data rate is possible with Bluetooth communications. But see, still we in mobile phones we are still using the Bluetooth technology. Bluetooth technology has been developed like 30, maybe 3 decades ago. Bluetooth technology. So unless and until there is a significant advantage or a significant development in technology, the underlying technologies or the already developed technologies is still being used because the standards have not been prepared for a very mature technologies. For example, when we are discussing about OTFS, there is nothing which has been standardized so far. So uh, how much is it lucrative, how much is it good to go for academic research? We will always see that in terms of usage, in terms of practical considerations, OFDM is still the technology which is being used so far, still the technology, because that is a technology which comes under the umbrella of regulations already. So only just technology. So standards are very important. That's what I'm trying to say. Again, the characteristics of VLC and RF. So VLC, by visible light communication, see the bandwidth is the unlimited bandwidth almost, and the RF bandwidth is limited, but the distance is very short and distance is very medium actually. You know, coverage is short, its coverage is very wide. So this is what the problem is. This is a trade-off. Life is a trade-off. Wish to have a very high, ultra massive data rates, ultra massive, transmission of data. So you need to compromise on something which is distance. If you go with very far off distances, so you need higher wavelengths, and wavelengths to lower bands, and your bandwidth becomes smaller, so data rates less incorporated on those bands. This is an example with 2G and 3G. 2G waveforms still they are for long distance communications for less infrastructure. 2G spectrum is very popular. But as you go on with 5G communications or infrastructure needs are higher. But in the same case, the quality or the high speed communication becomes possible with 5G. Okay. The last thing, which is actually intelligent reflecting surfaces, intelligent IRS technologies. So this is a technology where this is nothing but a printed coplanar glass structure which is mounted on a wall, just a glass structure. What happens is that the functionality of IRS is that when the signal comes is incident on that particular glass, it reflects the signal in a particular direction. This is the entire purpose of IRS. It reflects the signal in a particular direction. So we are actually creating more and more reflections in the scenario in the region so as to get better connectivity of the signals, right? In order to have better connectivity of the signals. See, there's a guy moving localization, so satellite signals are not able to reach the sky. So what happens is that signals getting reflected and getting back to him. And see that this guy is standing in a dead zone. He cannot receive signal. So what happens is that there's a printed glass coplanar structure on the wall. So signals getting reflected and getting reached to him. So in order to get, we are actually trying to mimic and to the wireless medium. We are trying to mimic the wireless medium. We are trying to enhance the number of reflections in the wireless medium to our advantage in order to get more connectivity and what do you say, uh, more connectivity, and all the technologies, all the use cases of vertical, say for satellite technologies or the towers, we want to stay connected to them. So it provides better connectivity and high speed communication as well. Okay, so this is one of the papers which has been published in IEEE Transactions on Communications. IRS technology, very popular in terms of academic research, but it's not been adopted yet. It's not been adopted yet because of the lack of standardization. Not adopted yet. We are still in the era of 4G. अभी भी 4G के era में ही है, because 5G equipments, they have now started to be prepared. It started to being constructed by different companies, but it's still in the era of 4G actually as of now. IRS. So in nutshell, integration of technology in 6G, amalgamation of different technologies as per some of the industrial experts. In non-terrestrial networks, combination with terrestrial networks, sensing signals with communication signals, space, air, ground integrated network, a very fancy thing. Satellite connected to UAV, to marine services, to hot air balloons, to mobile devices, to base stations, space, air, ground integrated networks, correct? This is what it is. Augmented mixed virtual reality into extended reality, queuing theory with information theory. So in different aspects of technologies and different areas of research, the amalgamation of technologies, this is what the underlying idea, what is the underlying idea behind the development of 6G is. So this is a very critical aspect. It is integration of technologies. हम maximum क्या कर सकते हैं? We are already on the paramount of everything, on the maximum of everything. Now developing something new out of that, it is little difficult, but getting used to or mixing or amalgamating different technologies as per the newer applications emerging, it is much more easier. This is what industry people think. Okay, so now this is something which is my idea, and I actually worked on this particular idea, which I have adapted from the standard, which is a digital video broadcasting standard implementation guidelines for myself, right? So to see that it's an integrated satellite terrestrial broadcast system. right? So this is a satellite as well as terrestrial base station. So all of these mobile base stations, satellite broadcast distribution, they are connected to each other in order to form a scenario of 100% connectivity, a scenario of speed communication. So signals can either be received from the satellite or from the terrestrial transmitter, but mobile at no point of time will face that it is in the region of outage. Not, it does not have a connectivity. Jungle mein kyun na ho, does not have any connectivity, so this is a problem. That so this is one idea. Another thing is a hybrid satellite terrestrial broadcast system where uh, you know signals from both ultra reliable ultra reliable low latency communication. So in terms of reliability, so mobile receiver receives signals from both the base station and as well as the satellite, and in turn it enjoys the inherent diversity to improve its reliability, right? So this is one of the another idea. So I can go on and on. This is the spread OFDM. This is a variant of OFDM in the 5G technology, spread OFDM based transmission system, where the I dived into the moving pictures experts group to transport stream, from the standards point of view, and then there are different signals for different in the television. You see that there are different channels. So those different channels are different frequencies basically. So on those different frequencies, there are certain, for example, Star Plus is going on, Z is going on, Sony is going on. So the data is actually multiplexed in the form of MPEG-2 TS standard as per the standards, given the packet structure and given the incoming bit stream, parallel bit streams. So what I did is that I took this as from the standards and mapped it onto a modulator, which is from the physical layer point of view. This is a OFDM modulator, so spread OFDM transmission, and then we try to process the signal from the to achieve the goal that we need to have a very significant signal to noise ratio at the receiver, and we can have a variable bitrate quality of service. So this is something which I tried to do and got this work. This is a simulator, got this work published in IEEE Transactions on Vehicular Technology a few years ago. And then so this is what it is. I'm not going into the details of all this because this is, I just wanted to show you that how analysis is actually done. So basically you see that there's a, this is the transmitter, these are the wireless channel. LMS is actually the land mobile satellite communication channel. There are various different channel proposals and distributions for those channels. And then what I did is that I passed on to the channel, which is actually a time generative channel, which is which followed a Markov process of following of switching from one state to another state to another. So this is actually what it is. And then I did some the analysis in order to transform the communication in a particular channel uh, as to transmitting as per my needs for variable bitrate communications. Derive these closed form similar to noise expressions, uh, taking all these MATLAB simulation parameters where sampling frequencies, all of these values and all of this analysis and everything. This is something which I have been motivated from the standards itself. I have taken digital video broadcasting satellite handle standard and then tried to do the analysis. So see that there is on the level of OFDM, it's a linear curve, which is actually a normal linear curve, and then when I go with spread OFDM, so using the technology of CDM and OFDM together, so I say that based on the spreading factor, I am able to get something which is not linear, but it is actually moving towards the non-error region when I increase my signal to noise ratio significantly better. So I wrote certain equations for that. This is a transmitter. This is actually the I50 and F50 kernels. modified for phase noise as well as Doppler effect. And this is actually my multi-code interference and inter-symbol interference. And then finally, I tried to derive my signal to noise ratios based on the variance and in the denominator and the numerator. Finally, the bit error rate, and then this is the channel estimation errors and stuff like that. So finally, I am able to receive that when there's this quality of service, variable bitrate quality of service from 4 RB, 4 times the parallel incoming streams to यानी 4 channels आपके पास या आपके पास 16 channels हैं. So how the BER is different BERs, how BER is performing based on the signal to noise ratios we achieve. Okay, so this is what it is. Fine. So this is a spectral efficiency curve, and fine. Anyway, so my basic my basic uh, reason for, I mean, my basic motive behind today's discussion is actually so that I can uh, express my knowledge and motivate the audience to pursue their research, but under the umbrella of standards, keeping the practical aspects and considerations in their own point of view. So so there are certain use cases for futuristic 6G. That is the use case. Matlab, the 6G can be utilized in some of these vertical industries. That is then automation industry, terahertz communication, internet of many things, security and privacy. There's something which is called as a physical layer security. Nowadays, you might be hearing about QKD, quantum key distributions, in using optics. We have already discussed about optics, cell-free networks, extended coverage. So these are some of the futuristic 6G technologies. Futuristic 6G, vertical industries, or which can have multiple use cases and multiple applications where 6G can be incorporated. So uh, at the end, what I say is that in conclusion, in nutshell, what we have discussed so far, that there's a cycle from sowing a seed. You propose a particular fundamental or particular technology, then it takes some time to mature itself. You work it as a study item, then there's a work item. You do research on the particular domain, and then you before commercializing, then there's a process of standardization where the technologies then gets standardized, and then it is finally pushed into commercialization. Right? So this entire cycle takes on something around 10 years to work. 10 years to work. So this is what the thing is, that how standards are important and necessary to fulfill some of the needs of the market, for the market demands. And then as academicians, what we do is that we push our ideas in the form of papers, so that on the later stage, the policymakers or the stakeholders, people from industry, academia, they sit together, they might have discussions based on the results that we already publish, and they someday they can form some of the standards and regulations, and finally something can be pushed into commercialization and it is ready to use, so that we can have it at our disposal to use, such as the mobile phones, the MIMO technology in mobile phones, something like that. Correct. So I mark the end of the presentation so far. I hope I have uh, not bored people as in the audience. So if anyone is interested, they are free to ask questions, if whatsoever, from the non-technical, technical background, whatever it is. Please go on. Is anyone there or everyone sleeping? Hello? Hello? Organizers? Hello, organizers? Anyone there? Subs Organizers? Anyone there? Oh, anyone with any question? You can write message to me on the email ID if you in there is any research question or anything that discuss anything you want to discuss. So please do write me an email on this email ID. I'll do my best to respond to you guys. Okay. So if there are no more questions, thank you very much for your time and cooperation. Thank you.